Let's look at two problems. 56. Part A of the drawing shows a bucket of water suspended from the pulley of a well. The tension in the rope is 92 newtons. Part B shows the same bucket of water being pulled up from the well at a constant velocity. What is the tension in the rope in Part B? Now, it might not seem that they give you enough information, but they actually give you a lot. Now, the forces acting on the first bucket are its weight and the two tensions from the rope. There are two tension forces because the rope is attached to the bucket handle at two places. These three forces must balance, which will allow us to determine the weight of the bucket. In Part B of the drawing, the bucket is again in equilibrium, and since it is traveling at a constant speed and therefore has no acceleration, the forces acting on this bucket are now its weight and a single tension force from the rope, because it is only attached to the rope from one place. So you have to first draw your body diagram for the first one with two tension forces pointing upward of the same newtons, same amount, and your weight pushing downward. So when you do this, and it has to be equal to 0 because it is in equilibrium, you see that 92 plus 92, which are pointing upwards, that's why they're positive, minus your weight, which is pulling you downward, will be equal to 0. And using that, you see that your weight is equal to 184 newtons. Now, Part B, you can use the same type of thinking. Since you only have one tension force pulling you upward and and your weight pulling you downward, you know that these two added together will have to give you a net force of 0 because it's in equilibrium. Therefore, T minus W will be equal to 0, so T is equal to W. And since you already know from Part A that your W is 184, you know that your tension will also be 184 newtons. Let's look at another problem. A worker stands still on the roof with a sloped angle of 36 degrees above the horizontal. He is prevented from slipping by a static frictional force of 390 newtons. Find the mass of the worker. Now, the hard part about this problem is drawing your free body diagram. So let's start with pointing. Your normal force will always be pointing upward, and your gravity will always be pointing downward, perpendicular downward. To your left, you will have the only x component of your net force, which will be equal to your static frictional force. So now, because you know that your static frictional force is the only one acting on the x, you can say that your static frictional force is equal to mass times gravity times sine of theta. Now, when you solve for m, you see that m is equal to your static frictional force over g sine theta, and you can just plug in values and see that your mass of the worker is 68 kilograms.